Hi everyone. In today's session, we shall discuss our Unit 4, Deflection of Beams. So this is the first part of your Unit 4. In this video, I would like to discuss Introduction to Deflection of Beams and derivation of differential equation for bending moment and the relationship between shear force and bending moment and deflection, and in just introduction to double integration method. So in practical engineering applications, when we use different components, we have to operate with different limits. So if the constraints are placed and the behavior of the components plays a key role, for that instance, for a particular point, let us suppose to operate within this, the value of the stress and deflection should not be the given particular value. So in some problems, the maximum shear stress may be strict to severe condition, but there may be a deflection. So in obvious, therefore, to study the methods, we can predict the loads of transfers. Since this is a form of loading, we generally go with the deflection of the beams. So before going to it, there are few assumptions to be undertaken for the differential equations under elastic curve. So the stress should be always proportional to strain. That is nothing but Hooke's law application. So this is equation is valid for the beams that stresses are not beyond the elastic limit. Okay, and the curvature should be very small, and any deflection related to shear deformation and the maximum shear stress should be neglected. It shows that the deflection due to shear deformations are usually small and hence to be ignored for the assumption while deriving. So now let us consider a beam which is initially straight like this. Okay, and when unloaded, if under the action of loads, the beam tends to deflect A to dash to B dash like this, and where in fact the axis of beam shape to be A dash and B dash, and it is customarily called as A dash B dash, and the curved axis for the elastic curve or the deflection curve. In case of transverse loads of beams, we know that bending moment equation as sigma by y is equal to m by I equal to E by R, which I mentioned here. If we took in the elastic line, the deflection curve is obvious at every point of difference. Hence, the slope will be varying from point to point. So we all know the slope, there is nothing but the distance from y-axis to the x-axis. So to express the deflected shape of the rectangular coordinates, let us take two axes x and y with respect to origin, and the beam y-axis shows the deflection. So the x-axis is origin and y shows the deflection of the beam. So at the ends of this element, let us consider a normal intersecting at point O. Okay, then we know that tan I is nothing but dy by dx. So where I is assumed to be tan I, that is I is nothing but slope dy by dx. So we know that from this curve ds, the slope distance is radius into distance of particular. So r into di. So ds is equal to dx. So ds is equal to dx r di. So di by dx is equal to 1 by r. So we know that there is a on substituting value of phi is equal to dy by dx. So d by dx of dy by dx is equal to 1 by r. So that is d square y by dx square is equal to 1 by radius of curvature. So from simple bending moment theory, m by equal to e by r. So m is equal to ei by r. So the basic differential governing equation of the beam can be taken as m is equal to ei. I is nothing but here we got it as d square y by 1 by r is nothing but d square y by dx square. So this is the differential equation of the elastic line of beam. So the where y is function of x defines the slope and the radius of curvature as it is frequently called. Sorry. So now let us discuss about the relationship between the shear force, bending moment, and deflection. So now let us take the bending moment differential equation, which I got here. dm by dx is equal to ei into d cube by dx square. Recalling, we know that the force is nothing but change in momentum with respect to x. So thus F is equal to ei into d cube by dx square, dx cube. We know that the load is nothing but force per perpendicular. So W is equal to minus dF by dx. So F is nothing but EI into d cube y by dx cube. So here if I substitute, W is equal to minus EI d power 4 by dx power 4. So where Y is the deflection of the load beam. So these are the important terms to be remembered, or while solving it will be helpful. So the first slope we already know that dy by dx. For bending moment, EI into d square y by dx square. And for finding the shear force, EI into d cube y by dx cube. And the load distribution can be identified with the help of EI into d power 4 by d power 4 y by dx power 4. So if we know the slope, I can find the bending moment, shear force, and load distribution of the beam. So methods for finding the deflection. So the deflection of the loaded beam can be obtained by various methods. So the one of the most important method is to finding by using double integration method. So the governing equation for the bending moment we know. So bending moment is EI into t square y by dx square. So I can write it as m by EI is equal to d square y by dx square. On first integration, I am getting the slope, if I'm not wrong. Why? Because on integrating the both sides, dy by dx is equal to integral mbi dy plus a. So this equation gives us the slope. On again integration, I can find the deflection. Why? Because y is nothing but the deflection. So y is equal to double integral m by EA into dx plus constant of a with respect to x is 1 is ax plus b, where a and b are the constants of integration to be evaluated, and these will be evaluated with respect to the boundary conditions of particular value of x. So these are the some important short and essay answers questions which was asked in your previous examinations. Thank you.